Welcome to the video lecture series on digital image processing. In today's lecture, we will discuss about some basic mathematical transformations, and we will see that how these mathematical transformations help us in understanding the imaging model and the image formation process by a camera. So, in our last lecture, we have learnt different distance measures. We have seen the application of the distance measure, which we have said that in addition to finding out the distance between two different points, the distance measures are also used to find out the distance transformation of a binary image, and using that distance transformation, we can find out the skeleton of the image, which gives a compact representation or compact description of the shape. We have also seen different arithmetic and logical operations that can be performed on two images, and we have also seen what are the different neighborhood operations that can be performed on a single image. So, in today's lecture, as we said that we will discuss about some basic mathematical transformations, which will include translation, rotation and scaling, and this we will discuss both in 2 dimension as well as in 3 dimension. We will also discuss about the inverse transformations of these different mathematical transformations. We will find out the relationship between the Cartesian coordinate system and an homogeneous coordinate system, and we will see that this homogeneous coordinate system is very useful while discussing about the image formation by a camera. We will also talk about the perspective transformation and imaging process, and then we will talk about the inverse perspective transformation. Now, coming to the basic mathematical transformations, let us first talk about that what is the translation operation, and we will start our discussion with a point in 2 dimension. So, you know that if I have a 2 dimensional coordinate system given by the axis x and y, and if I have a point P which is having a coordinate given by say x y, and I want to translate this point P x y by a vector x naught y naught. So, after translating this point by the vector x naught y naught, I get the translated point say at point P prime, whose coordinates are x prime and y prime. And because the translation vector in this case we have assumed as x naught y naught, so you know that after translation the new position x prime will be given by x plus x naught, and y prime will be given by y plus y naught. Now, so this is the basic relation when a point at location x y is translated by a vector x naught y naught. Now, let us see that how this can be represented more formally by using a matrix equation. So, if I translate this equation in the form of a matrix, the equation looks like this. I have to find out the new location vector x prime y prime, and we have said that this x prime is nothing but x plus x naught, and y prime is nothing but y plus y naught. So, this particular relation, if I represent in the form of a matrix, it will simply look like this. So, you find that if you solve this particular matrix expression, it gives you the same expression x prime equal to x plus x naught and y prime is equal to y plus y naught. So, on the right hand side you find that I have product of two matrices which is added to another column matrix or column vector. Now, if I want to combine all this operation in a single matrix form, then the operation will be something like this. On the left hand side, I will have x prime and y prime, which will be in the form of a matrix, and on the right hand side, I will have 1, 0, then x naught, 0, 1, y naught, and then I will have x, y, and 1. So, if I again do this same matrix computation, it will be x prime equal to x plus 0 plus x naught. So, which is nothing but x plus x naught. Similarly, y prime will be 0 plus y naught, which is nothing but y plus y naught. But you find that in this particular case, there is some asymmetry in this particular expression. So, if I want to make this expression symmetric, then I can write it in this form x prime y prime, and I introduce one more component which I make equal to 1. This is equal to 1 0 x naught, 0 1 y naught, then 0 0 1 and x y 1. So, find that this second expression which I have just obtained from the first one is now a symmetric expression, and this is what is called an unified expression. So, find that basically what I have is I had the original coordinate x y of the point P, which is appended with one more component that is given as 1, and if this modified coordinate is now transformed by a transformation matrix which is given as 1 0 x naught, 0 1 y naught and 0 0 1, then I get the translated point as x prime y prime 1, where if I just neglect the additional component, which in this case is 1, then I get the translated point P prime. So, this is about the translation. In the same manner, given a point P, again in 2D, so again I have this point P, which is having a coordinate x y, and suppose I want to rotate this point P around the origin by an angle theta. Now, one way of representing this point P is, if r is the distance of point P from the origin, then these are the coordinates of the point P. This is the x coordinate, this is the y coordinate. So, I can also represent, and suppose this angle is alpha, then I can also represent x as x equal to r cosine alpha and y equal to r sin alpha. Now, suppose I want to rotate this point P by an angle theta in the clockwise direction. So, the new position of P will now be P prime, having the coordinate location x prime and y prime, and this rotation angle of rotation is now angle theta. So, our job is that what will be these points, the coordinate points x prime and y prime. So, here you find that I can write this x prime as r cosine alpha minus theta, and I can write y prime as r sine alpha minus theta. Okay. So, if I simply expand this, so I have x prime is equal to r cosine alpha minus theta and y prime is equal to r sine alpha minus theta. So, if I simply expand this cosine term, it will simply be r cosine alpha cosine theta plus r sine alpha sine theta. Now, we know that r cosine alpha is nothing but x. So, it becomes x cosine theta plus r sine alpha is nothing but y. So, it becomes y sine theta. Similarly, in this case, if I expand this, it becomes r sine alpha cosine theta minus r cosine alpha sine theta. So, again r sine alpha, this is nothing but y. So, this takes the expression y cosine theta minus x sine theta. So, again, so here I find that x prime is given by x cosine theta plus y sine theta and y prime is given by minus x sine theta plus y cosine theta. So, even now, if I represent this in the form of a matrix equation, it becomes x prime y prime is equal to cosine theta sine theta, then minus sine theta cosine theta, and then I have the original coordinates x and y. So, here you find that if I rotate the point P by an angle theta around the origin in the clockwise direction, in that case the transformation matrix which gives you the rotation transformation is given by this particular matrix, which is cosine theta sin theta minus sin theta cosine theta. Now, in the same manner, if I go for scaling, say for example, if I have a scaling Sx, scaling factor of Sx in the x direction, and I have scaling factor Sy in the y direction, in that case the transformation matrix for scaling can also be represented as x prime y prime is equal to Sx 0 0 Sy and which is multiplied by the original coordinate x y. So, here you find that the transformation matrix for performing the scaling operation is nothing but the matrix Sx 0 and 0 Sy. So, these are the simple transformations that I can have in 2 dimension. Now, it is also possible to concatenate the transformations. For example, here I have considered the rotation of a point around the origin. Now, if my application demands that I have to rotate the point P around an arbitrary point Q in the 2 dimension, then finding out the expression for this rotation of point P by an angle theta around another point Q is not an easy job. I mean, that expression will be quite complicated. So, I can simplify this operation just by translating the point Q to the origin, and the point P also has to be translated by the same vector, and after performing this transformation, the translation, if I now rotate point P by the same angle theta, and now it will be the rotation around the origin. So, whatever expression that we have found here, that is cosine theta sin theta minus sin theta cosine theta, the same transformation matrix will be applicable. And after getting this rotation, now you translate back the rotated point by the same vector, but in the opposite direction. So, here the transformations that we are applying is, first we are performing a translation of point P by the vector, and after performing this translation we are performing the rotation. So, this is your transformation say r theta. So, first we are translating by a vector say r, then we are performing a rotation by vector r theta, and after doing this, whatever point I get, that has to be translated back by minus r. So, I will put it as translation by the vector minus r. So, this entire operation will give you the rotation of a point P. Suppose this is point P and I want to rotate this around the point Q. So, if I want to rotate P around Q by an angle theta, then this operation can be performed by concatenation of this translation, rotation, then followed by inverse translation, which puts back the point to its original point where it should have been after rotating around point Q by angle theta. So, these are the different transformations, the basic mathematical transformations that we can do in a two-dimensional space. Now, let us see that what will be the corresponding transformations if I move from two-dimensional space to the three-dimensional space. So, the transformations in the 3D coordinate system that we will consider is translation, rotation and scaling, and the coordinate system that we will consider in this case is three-dimensional coordinate system. So, first let us see, as we have seen in case of two dimension, that if a point x, y, z is translated to a new coordinate, say x star, y star, z star, using a displacement vector x naught, y naught, z naught, then these translated coordinates x star will be given by x plus x naught, y star will be given by y plus y naught, and z star will be given by z plus z naught. So, you see that in our previous case, we have said that because we had only the coordinates x and y. So, this third expression z star is equal to z plus z naught, that was absent. But now, we are considering a three-dimensional space, a 3D coordinate system. So, we have three coordinates x, y and z, and all these 3D coordinates, all these three coordinates are to be translated by the translation vector x naught, y naught, z naught, and the new translation vector and the new point we get as x star, y star and z star. Now, if I write these three equations in the form of a matrix, then the matrix equation will be like this: x star, y star, z star on the left hand side will be equal to 1 0 0 x naught, 0 1 0 y naught, 0 0 1 z naught into the column vector x y z 1. So, this is the similar situation that we have also seen in case of two dimension, that we have to add an additional component which is equal to 1 in our original position vector x y z. So, in this case again we have added the additional component which is equal to 1. So, our next position, our new position vector becomes x y z 1, which has to be multiplied with the translation matrix given by 1 0 0 x naught, 0 1 0 y naught and 0 0 1 z naught. So, again as before, we can go for an unified expression where this translation matrix, which at this moment is having a dimension 3 by 4, that is, it is having 3 rows and 4 columns. In unified representation, we will represent this matrix, the dimension of the matrix will be 4 by 4, which will be a square matrix, and the left hand side also will have the same unified coordinate, that is x star, y star, z star 1. So, the unified representation, as we have already said, is given by x star, y star, z star 1 is equal to the translation matrix 1 0 0 x naught, 0 1 0 y naught, 0 0 1 z naught, 0 0 0 1 multiplied by the column vector x y z 1. So, this particular matrix, that is 1 0 0 x naught, 0 1 0 y naught, 0 0 1 z naught and 0 0 0 1. This represents a translation, a transformation matrix used for the translation, and we will represent this matrix by this uppercase letter T. So, that is about the simple translation that we can have. So, in our unified matrix representation, we have done that if you have a vector V, a position vector V, which is translated by the transformation matrix A, the transformation matrix A is a 4 by 4 transformation matrix. The V, if the original position vector was x, y, z, we have added an additional component 1 to it in our unified matrix representation. So, V now becomes a 4 dimensional vector having components x, y, z and 1. Similarly, the transformed position vector V star is also a 4 dimensional vector which is having components x star, y star, z star and 1. So, this is how in the unified matrix representation we can represent the translation of a position vector or a translation of a point in 3 dimension. Similarly, we can have, so as I said that this is the transformation matrix which is represented, which is used for translating a point in 3D by vector x1, y, x naught, y naught, z naught, or the displacement vector x naught, y naught, z naught. Similarly, as we have seen in case of scaling in 2 dimension, that if we have the scaling factor of Sx, Sy and Sz along the directions x, y and z. So, along direction x we have the scaling factor Sx, along direction y we have the scaling factor Sy, and along the direction z we have the scaling factor Sz. Then the transformation matrix for this scaling operation can be written by S equal to x Sx 0 0 0, then 0 Sy 0 0, then 0 0 Sz 0, then 0 0 0 1. So, here again if you find that a position vector x, y, z in unified form it will be x, y, z 1. If that position vector is translated by this scaling matrix, then what we get is the new position vector corresponding to point x, y, z 1 in the scaled form. And there if we remove the last component that is equal to 1, what we get is the scaled 3D coordinate of the point which has been scaled up or scaled down. So, it will be scaling up or scaling down depending upon whether the value of the scale factors are greater than 1 or they are less than 1. Then coming to rotation, we have seen that the translation and scaling in 3 dimension is very simple. It is as simple as we have done in case of 2 dimension, but the rotation in 3 dimension is a bit complicated, because in 3 dimension as we have 3 different axes, x axis, y axis and z axis. So, when I rotate a point around origin by certain angle, the rotation can be around x axis, the rotation can be around y axis, the rotation can also be around z axis. So, accordingly I can have 3 different rotation matrices for representing rotation around a particular axis. And specifically, if the rotation has to be done about an arbitrary point, then what we have to do is we have to translate the arbitrary point to the origins by using the translation transformation. After translating the points to the origin, then we have to perform rotation around the origin, then we have to translate back the point to its original position. So, which gives us the desired rotation of any point P in 3D around any other arbitrary point Q also in 3D. So, now let us see that how this rotation will look like in 3D. So, here you find that we have shown on the right hand side this particular figure, where this this figure shows the rotation of the point along x axis. So, if the point is rotated along x axis, the rotation is given by is indicated by alpha. If it is rotated along z axis, the rotation is indicated by theta, and if the rotation is done along y axis, the rotation angle is indicated by beta. So, if I rotate the point along z axis, so when I am rotating a point along z axis, then obviously the z coordinate of the point will remain unchanged even in the rotated position. But what will change is the x coordinate and y coordinate of the point in its new rotated position. And because the z coordinate is remaining unchanged, so we can think that this is a rotation on a plane which is parallel to the xy plane. So, the same transformation which we have done for rotating a point in 2 dimension in the xy coordinate, the same transformation matrix holds true for rotating this point in 3 dimension along the axis z. But now, because the number of components in our position vector is more, so we have to take care of the other components as well. So, using this, you find that when I rotate the point around z axis, the rotation angle is given by theta, and the rotation matrix is given by cosine theta, sin theta 0 0, minus sin theta, cosine theta 0 0, then 0 0 1 0 and 0 0 0 1. So, this is the transformation matrix or rotation matrix for rotating a point around z axis. So, here you find that the first few components, that is cosine theta, sin theta, then minus sin theta and cosine theta. So, this 2 by 2 matrix is identical with the transformation matrix or rotation matrix that we have obtained in case of 2 dimension. So, this says that because the z coordinate is remaining the same, so the x coordinate and y coordinate due to this rotation around z axis follows the same relation that we have derived in case of 2 dimension. Similarly, when I translate the point around y axis, where the rotate the point around y axis, the angle of rotation is given by beta. So, r beta as given in this particular case gives you the rotation matrix, and if you rotate the angle around x axis, where the rotation angle is given by alpha, you find that r alpha gives you the corresponding rotation matrix along the corresponding transformation matrix for rotation along the x axis. So, as before, here you find that when you rotate the point around x axis, the x coordinate will remain the same, whereas the y coordinate and the z coordinate of the point is going to differ. Similarly, when you rotate the point around y axis, the y coordinate is going to remain the same, but x coordinate and z coordinate, they are going to be different. Now, as we have also mentioned in case of 2 dimension, that different transformations can be concatenated. So, here we have shown that how we can concatenate the different transformations. Here you find that all the transformations that we have considered in 3 dimension, all of them are in the unified form. That is, every transformation matrix is a 4 by 4 matrix, and all the coordinates that we consider, we add 1 to the coordinate x, y, z, so that our position vector becomes a 4 dimensional vector, and the translated point is also a 4 dimensional vector. So, if I want to concatenate these different transformations, that is translation, scaling and rotation, and if I want to rotate a point about z axis, then this translation, scaling and rotation, this can be concatenated as: first you translate the point v by the translation operation t or the translation matrix t, then you perform scaling then you perform rotation, and this rotation is r theta, and all these three different transformation matrices that is r theta, s and t, all of them being 4-dimensional matrices, can be combined into a single matrix. So, this single transformation matrix, in this case A, which is nothing but the product of r theta, s and t, and this A again will be a matrix of dimension 4 by 4. Now, you note that whenever we are going for concatenation of the transformations, the order in which these transformations are to be applied, that is very, very important, because these matrix operations are in general not commutative. Now, just to illustrate that these matrix operations are not commutative, let us take this example. Suppose I have this particular point V, and to this point V I want to perform two kind of operation. One is translation by a vector. So, the translation vector we have represented by this arrow by which this point has to be translated, and the point V is also to be rotated by certain angle. Now, there are two ways in which these two operations can be done. The first one shows that suppose I rotate point V first by using the operation R V. So, here the transformation matrix is A R for the rotation operation, and after rotating this point V by using this transformation R, I translate the rotated point by using the transformation matrix T. So, if I do that, you find that this V is the original position of this point. If I first rotate it by using this rotation transformation, the point V comes here in the rotated position, and after this, if I give translation to this point V by this translation vector, then the translated point is coming over here, which is represented by V 2. So, the point V 2 is obtained from V first by applying the rotation by transformation R, followed by applying the translation by the transformation T. Now, if I do it reverse, that is, first I translate the point V using this transformation T, and after this translation I rotate this translated point, which is now T V, by the same angle theta. So, what I do is, first I translate the point using the transformation T, and after that this translated point is rotated by using the rotation transformation R, and this gives me the rotated point or the new point that is equal to V 1. Now, from here you find that in the earlier case where I got the point V 2 and now I get the point V 1, this V 1 and V 2, they are not the same point. So, this clearly illustrates that whenever we go for concatenation of different transformations, we have to be very, very careful about the order in which these transformations are to be specified or the transformations are to be applied, because if the order in which the transformations are applied vary, then we are not going to get the same end result. So, for any such concatenation, the order in which the concatenation is applied, the transformations are applied, that has to be thought of very, very carefully. So, that is about translation of the transformation of a single point. Now, if I have to transform a set of points, say for example, I can have a square figure which says like this. Say for example, in a two-dimensional space x, y, I have a square figure like this. So, these will have 4 vertices. The vertices I can represent as point P1, point P2, point P3 and point P4. Now, so far the transformations that we have discussed, that is the transformation of a single point around origin or the transformation of a single point around another arbitrary point in the same space. Now, here if I have to transform this entire figure, that is, for example, I want to rotate this entire figure about the origin, or I want to translate this entire figure by certain vector, say v. So, say for example, I want to translate this entire figure to this particular position. So, you find that here all these points P1, P2, P3 and P4, all these points are going to be translated by the same displacement vector v. So, it is also possible that we can apply transformation to all the points simultaneously rather than applying transformation to individual points one by one. So, for a set of m points, what we have to do is we have to construct a matrix V of dimension 4 by m. That is, every individual point will now be considered of course, in the unified form will now be considered as a column vector of this matrix, which is of dimension 4 by m. And then we have to apply the transformation A to this entire matrix, and the transformation, after this transformation we get the new matrix V star, which is given by the transformation A multiplied by the matrix V. So, here you find that any particular column, the ith column in the matrix V star, which is a Vi star, is the transformed point corresponding to the ith column of matrix V, which is represented by Vi. So, if I have a set of points which are to be transformed by the same transformation, then all those points can be arranged in the form of columns of a new matrix. So, if I have m number of points, I will have a matrix having m number of columns. The matrix will also obviously have 4 rows, and this new 4 by m matrix that I get, this entire matrix has to be transformed using the same transformation operation, and I get the transformed points again in the form of a matrix. And from that transformed matrix, I can identify that which point, which is the transformed point of the original point. Now, once we get these transformations, again we can get the corresponding inverse transformations. So, the inverse transformations in most of the cases can be obtained just by observation. Say for example, if I translate a point by a displacement vector v, then inverse transformation should bring back that translated point, that transformed point, to its original position. So, if my translation is by a vector v, the inverse transformation or the inverse translation should be by a vector minus v. So, the inverse transformation matrix T inverse can be obtained as 1 0 0 minus x naught, 0 1 0 minus y naught, 0 0 1 minus z naught, then 0 0 0 1. So, you remember that the corresponding transformation matrix that we said was 1 0 0 x naught, 1 0 0 0 1 0 y naught, 0 0 1 z naught and 0 0 0 1. So, you find that x naught, y naught and z naught, they have just been negated to give you the inverse translation matrix T inverse. So, similarly, by the same observation, we can get inverse rotations, the r theta inverse, where what we have to do is, in the transformation matrix, original rotation matrix, we had the term cosine theta, sin theta, minus sin theta, cosine theta. Now, all these thetas are to be replaced by minus theta, which gives me the inverse rotation matrix around the z axis. Similarly, we can also find out the inverse matrix for scaling where the Sx will be replaced by 1 upon Sx. So, these are the basic transformations, basic mathematical transformations. Now, we will see another form of transformation, which is called a perspective transformation. Now, this perspective transformation is very, very important to understand how a point in the 3 dimension, in the 3D world is imaged by a camera. So, this perspective transformation is also known as an imaging transformation, and the purpose of this imaging transformation is to project a 3D point, a 3D world point into the image plane, and this gives an approximation of to the image formation process, which is actually followed by a camera. Now, let us see what is this perspective transformation. Here we have shown a figure which is an approximation of the image formation process. Here you find that we have 2 coordinate systems which are superimposed one over the other. One is the 3D world coordinate system represented by capital X, capital Y, capital Z. So, this is the 3D world coordinate system, capital X, capital Y and capital Z, and I also have the camera coordinate system, which is given by lowercase x, lowercase y and lowercase z. Now, here we have assumed that this camera coordinate system and the 3D world coordinate system, they are perfectly aligned. That is, x axis of the 3D world coordinate system coincides with the x axis of the camera coordinate system, y axis of the world coordinate system coincides with the y axis of the camera coordinate system. Similarly, z axis of the world coordinate system coincides with the z axis of the camera coordinate system. So, they have both these coordinate systems have the same origin. Now, if I have a point x, y, z in 3D. So, this is the point x, y, z in 3 dimension, and I assume that the center of the lens is at location 0, 0, lambda. So, obviously, the lambda, which is the z coordinate of the lens center, this is also nothing but the focal length of the camera. And this x, y, z, this particular 3D point, we assume that it is mapped to the camera coordinate given by lowercase x and lowercase y. Now, our purpose is that if I know this 3D coordinate system capital X, capital Y, capital Z, and I know the value of lambda, that is the focal length of the camera, whether it is possible to find out the coordinate, the image coordinate corresponding to this 3D world coordinate x, y, z. So, to this we apply the concept of similar triangles. So, here what we do is, by using the similar triangles, we can find out an expression that lowercase x by lambda is equal to minus capital X by capital Z minus lambda, which is nothing but capital X by lambda minus Z, and y by lambda is in the same manner is given by capital Y by lambda minus capital Z. So, from this I can find out that the image coordinates of the 3D world coordinate capital X, capital Y, capital Z is given by x coordinate x, image coordinate x is given by lambda x by lambda minus capital Z. Similarly, the image coordinate y is given by lambda capital Y divided by lambda minus capital Z. Now, this expression also can be represented in the form of a matrix, and here we will find that if I go for homogeneous coordinate system, then this matrix expression is even simpler. So, let us see what is this homogeneous coordinate system. Homogeneous coordinate system is, if I have the Cartesian coordinate capital X, capital Y, capital Z, then we have said that in unified coordinate system we just append a value 1 as an additional component. Homogeneous coordinate system is, instead of simply adding 1, we add an arbitrary non-zero constant, say k, and multiply all the coordinates x, y and z by the same value k. So, given the Cartesian coordinate capital X, capital Y, capital Z, I can convert this to homogeneous coordinate by k times capital X, k times capital Y and k times capital Z. The inverse process is also very simple, that if I have a homogeneous coordinate, then what I have to do is, I have to divide all the components of this homogeneous coordinate by the fourth term. So, in this case the fourth term is k and all the other terms were kx, ky and kz. So, if I divide all these three terms by the fourth component k, I get the Cartesian coordinate x, y, z. So, I can convert a 3D point, the coordinates, from the Cartesian coordinate system to the homogeneous coordinate system, and I can also very easily convert from homogeneous coordinate system to Cartesian coordinate system. Now, to understand the imaging process, let us define a perspective transformation which is given by p equal to 1 0 0 0, 0 1 0 0, then 0 0 1 0, then 0 0 minus 1 upon lambda. You remember this lambda is the focal length of the camera, and then 1. And we translate our world coordinate w to the homogeneous coordinate. So, it becomes kx, ky, kz and k. Now, if I transform this homogeneous world coordinate by this perspective transformation matrix P, then I get the homogeneous camera coordinate ch, which is given by kx, ky, kz, then minus k into z by lambda plus k. So, this is the homogeneous camera coordinate. Now, if I just convert this homogeneous camera coordinate to the Cartesian camera coordinate, I find that the Cartesian camera coordinate is given by c equal to small x, small y, small z, which is nothing but lambda x divided by lambda minus z, lambda y divided by lambda minus z and lambda z divided by lambda minus z. So, on the right hand side, this x, y, z, they are all in uppercase, indicating those are the coordinates of the world point. Now, if I compare these expressions with the camera coordinate that we have obtained with respect to our previous diagram, you find that here we get lowercase x is nothing but lambda capital X divided by lambda minus z. Similarly, lowercase y is also nothing but lambda capital Z by lambda minus z. So, using our previous diagram, we have also seen that these lowercase x and lowercase y, they are the image points on the image plane of the world coordinate capital X, capital Y and capital Z. So, this shows clearly that using the perspective transformation that we have defined as the matrix P, I can find out the image coordinates of a world coordinate point capital X, capital Y, capital Z following this particular transformation P. Now, here in this particular case, the third component that we have obtained, that is the value of z, which is not importance in our case, because in the camera coordinate the value of z is always equal to 0, because we are assuming that the imaging plane is the x y plane of the world coordinate system as well as the camera coordinate system. So, we will stop our discussion here today, and in the next class we will see that as we have seen that with the perspective transformation, we can transform a world coordinate, we can project a world point, a 3D world point onto an imaging plane. Similarly, using the inverse perspective transformation, whether it is possible that given a point in the image plane, whether we can find out the corresponding 3D point in the 3D world coordinate system. So, now let us discuss about the questions that we had given at the end of lecture 5. The first question that was asked is, there was a figure showing 2 points P and Q, and the question was, you have to find out which of the options are true, that is whether Q is a 4 neighbor of P, Q is a 8 neighbor of P, or Q is a diagonal neighbor of P. Now, here you find that in this particular figure, when you look at the locations of P and Q, the 4 neighbors of P are the 2 points which are vertically upward and downward, and the 2 points which are horizontally to the left and to the right. But the point Q is in the diagonally upward direction of point P. And we have said that all the 8 points around point P, they form the 8 neighbors of point P. So, in this particular case, the point Q, which is a diagonal neighbor of point P, and it is also one of the 8 neighbors of point P. So, the options B, that is Q belongs to N8P and Q belonging to NDP, both these options are true, whereas the option A, that Q belongs to N4P, that is wrong. The second question is quite obvious, quite simple. You have to find out the Euclidean distance, city block distance, and chessboard distance between the 2 points P and Q. So, this is a very simple question. You can try it yourself. Let us go to the third question. Here we have given 2 sub images S1 and S2, and you have to determine whether S1, S2 are 4 connected, 8 connected, or M connected. If you remember, when we discussed about the connectivity, we have said that 2 images are 4 connected, 2 sub images are 4 connected, if there is any point in one of the sub images which is 4 connected to a point in the other sub image. In this particular case, you find that there is no point in S1 which is 4 connected with a point in S2, and similarly there is no point in S2 which is 4 connected to a point in S1. So, S1 and S2, they cannot be 4 connected. But here you find that I have a point in S1 said here, and there is a point in S2 here. These 2 are actually connected, but they are not 4 connected. So, these 2 points are connected. We can say that these 2 points are connected in 8 connected sense, because this point is an 8 neighbor of this point. Similarly, this point is also an 8 neighbor of this point. And at the same time, these points are also connected in M connected sense, because there is no common 4 neighbor of this point and this point. So, you can say that these image regions S1 and S2, they are both 8 connected as well as M connected, but these 2 regions S1 and S2, they are not 4 connected. Now, coming to the next question, here we had given a binary picture, binary image, and you were asked to find out what is the skeleton of this binary image. Now, you remember that when we had discussed about the skeletonization of any binary figure, the first operation that we had done was the distance transformation of that particular figure. Now, here if I find out the distance transformation, you find that all these boundary points, they will get a distance value equal to 1. Similarly, these points will also get distance values equal to 1. The other points, these points will get distance values equal to 2. These points will also get distance values equal to 2. So, once in this manner, if you find out the distance values at every point, then from that distance transformation you can find out the points where there is curvature discontinuity, and we have said that the points of curvature discontinuity, they form the skeleton of the particular image. So, now let us see have some quiz questions on today's lecture. The first question is, what is the concatenated transformation matrix for translation by a vector 1 1 followed by rotation by angle 45 degree in 2 dimension? The second question is, here there is a figure, a square with 4 corners. So, if this figure is first scaled by factor 2 and then translated by vector 2 2, what is the transformed figure? Third question, determine the figure if the translation is applied first followed by scaling. Fourth question, a unit cube with vertices 0 0 0, 0 0 1, 0 1 0, 0 1 1, 1 0 0, 1 0 1, 1 1 0 and 1 1 1 is scaled using Sx equal to 2, Sy equal to 3 and Sz equal to 4. Then what are the vertices of the transformed figure? The fifth one, a camera lens has a focal length of 5. Find out the image point corresponding to a world point at location 5700. Assume the image coordinate system and the world coordinate system to be perfectly aligned. Thank you.